Dr. Channel. Thank you for the introduction. Good morning, everyone. Welcome to our presentation. My name is Haoqi Shan, and I will be representing my colleagues from University of Florida and University of New Hampshire to present our work today, the invisible finger, a practical electromagnetic interference attack on touchscreen devices. So what exactly is our attack? And in short, invisible finger is a remote precise touch event injection attack against a capacitive touchscreen device using IEMI signal. So in detail, there are some characteristics associated with our attack. For instance, our attack can be used to inject touch events on touchscreen devices from a distance up to 3 centimeters. And our attack can induce short tap, long press, omnidirectional swipe on touchscreen devices as well. So it also works on different type of device, touchscreen device with respect to different scanning and driving mechanism, things like that. And comparing with previous touchscreen attacks, it is also practical attack with a combination of our screen locators, our touch event detectors, and we also build a website, to introduce our attack in detail. And also there are some video demonstrations, so if you're interested, please go ahead and check it out later after this presentation, all right? So before we jump into the meat of our presentation, I want to show a quick video demonstration to give a hint on what we can achieve using our attacks, okay? So once we generate a sufficient IEMI signal with certain parameters, say frequency, voltage, amplitude, signal shape, things like that, and we can generate a short tap to induce keystrokes, we can also turn that into a long press, and we eventually can turn into that any duration omnidirectional swipe, as you can see on the screen. And you can also notice that there are the 3 acrylic shakes between the antennas and between our target device. So you can see like the attack is launched from the remote, from a distance. So, 1 second. In detail today, we will be going through, for example, a bit of background knowledge and theoretical analysis on touchscreen devices and how to generate a precise touch event. And finally, we'll go to how do we conduct a practical attack using such techniques. So for modern capacitive touchscreen, which everyone is using right now, probably you're holding that in your hands right now, and there are 2 main types of capacitive touchscreen sensor technology, self-capacitive and mutual capacitive sensors. So a self-capacitive system measures the change in capacitance with respect to the Earth's ground, while on the contrary, the mutual capacitive touchscreen devices, which allows the use to use 2 electrodes together, and then it measures the capacitance change when user finger touches it. So in our work, we mainly target on mutual capacitance touchscreen, as it's actually going to be the major capacitance technology that has been used widely in the field. So once we have a proper target that we decide to attack, now let's take a look at this fundamentally, how mutual capacitance touchscreen works. So the mutual capacitance touchscreen often consists with multiple pairs of transmitting and receiving electrodes and excitation signal generator, QT sensor, ADC, and microprocessor, etc. And when a human finger is presented on the touchscreen, so it alters the current capacitance of the touchscreen. And this change can be either positive, can be either negative, really depends on human impedance variation. And so now we can see that fundamentally, all things this capacitance touchscreen just measure the capacitance and see if it changes. If it changes, then there's a finger touch. That's it, right? So it's pretty simple. But internally, how does this mechanism is implemented in circuit level? So here we show a simplified version of the touchscreen design, which is also known as a charge transfer circuit topology. And on the left side, we can see that we use a voltage source to represent how electrodes on touchscreen is charged by excitation signal. And on the right side, we can see there's an op-amp design to turn this kind of capacitance of the mutual capacitor, CM, into a voltage VO, where it can just use ADC and such to measure it. And so this is why it's actually called charge transfer circuit, because the CM gets charged and then the capacitance is transferred to CS afterwards. So in order to make this circuit working properly, the switch of the charge transfer topology needs to be coordinated and be switched on and off in a pattern. And in general, these different switch will be on and off, based on the charging period, sensing period, resetting period, and such. The frequency of this switching signal is also important to conduct attack, which we will discuss later. So now we know that human fingers touch this. If the human finger touches the screen, then there will be capacitance change. But what about when we have the EMI noise? So the EMI noise that is directly applied on the touch screen is equivalent to a tiny voltage source that interferes with the capacitance sensing part and eventually be recognized as the voltage change and the finger touch. So now we have a sufficient idea on what is a touch screen and how exactly it works, and what makes our work different than previous approaches. So we know that IEFI works in theory, to act like fingers, but what kind of EMI signal actually works and can be recognized as a touch event? So here comes one of our major contribution. We couple the theoretical analysis and the actual attack vectors. As we see before, that the charge transfer sensor, also known as QT sensor, measures the capacitance, right? And if there's a finger touch, the capacitance changes, the voltage change. The voltage output of OPM changes, if there's touch. So now let's say if we are using a sine wave IEMI signal as a VN, perform this similar approach, and we can also see the measured voltage changes and the pass the threshold. And basically, in theory, we just induce a touch event. Using our current model, we can get the needed amplitude and the frequency to induce enough voltage changes, and that can be recognized as a touch event. Although we don't really show a very detailed duration process over here, because like in the paper, we spent like 2.5 pages on doing that, so we don't have enough time today. But the needed voltage is actually associated with the mutual capacitance, charge transfer capacitance, and QT sensor switching frequency, and the switching signal duties, etc. So we also provide the needed frequency here, but you should notice that most importantly, that the frequency of inducing a successful attack is actually not unique. There's multiple frequency, based on our theoretical analysis. There's multiple frequency can be used to induce a successful touch event. But that's just a theory, right? We need to validate, right? So how do we validate our model and analysis? We use a Chromebook, which is equipped with touchscreen diagnostic software to perform the data collection, and while we're applying the IEMI signal. And we use 2 copper plates, one's on the front of the panel, the lead, and one's on the another one is on the back side of it to induce the IEMI signal as the antenna. So the Chromebook diagnostic software will tell us when, where, and how touch event is generated. So now we can try all the combination of the E field, the strength, the frequency, and see if our equation is correct or not, right? So by recording the minimum E field and associated frequency that we can induce the touch event, we can notice that there's a pattern of the recorded E field, which is aligned with our equation and our analysis. So it worth mentioning that different touch event, different touch screen will have like different parameters, and the design is a little bit different, but still our analysis will just allow us to narrow down what could be the combination of the E field strengths and what could be the IEMI signal attack frequency. So you can just perform this kind of attack quick and fast. So once we know how to generate the touch event using our calculated IEMI signal parameter, and we now need to resolve the issue. How do we make this attack accurate and precise? So comparing with previous approach, which was published on SMP and Usenix recently, another one of our major contributions lies on generating a precise touch event and conducting thorough experiments. So what is the challenge exactly, of generating a precise touch event? The challenge comes from sensing and driving mechanism used by different touchscreen controller. In general, there are 2 types of the method to perform scanning or driving on electro grid. So one of them is sequential, and one of them is parallel. So the sequential scanning mechanism will excite the X or Y electrodes one by one, and then sense each line on Y or X electrodes respectively. And where the parallel scanning will try to encode this excitation signal and drive the X or Y electrodes on the same time, and then censor the other side of the electrodes and try to measure the capacitance. So on these slides, we can also see how this kind of driving signal actually looks like, on real device. One of them is collected on iPhone 11 Pro, and another one is collected on Pixel with respect to parallel and sequential driving mechanism. So the previous approach generally only works on, on sequential driving mechanism, where because there's a certain pattern, and this pattern is actually pretty easy to identify, right? So the attacker can measure the driving signal and choose what is the correct timing to inject that IEMI signal. And however, for example, just like this, like the attacker are trying to measure and see, okay, this is the time this column or this row is measured, this is excited, I'm going to inject IEMI signal at this precise moment to make this touch event precise. But as you can also see, because the parallel scanning is all on the same time, so it won't really work when the touchscreen uses embedded parallel driving mechanism. So our attack, which on the contrary does not require a particular driving mechanism, instead we use antenna design where it can generate actually a very focused field to apply the interference on the very specific and narrow region on your touchscreen. And we apply this appropriate EMI signal, and we wait for that place to be scanned by the touchscreen controller, which is just like human fingers, right? So your fingers is actually pressing the screen, and it will be scanned sometime. And we are basically mimicking the same way that works. So just like a human finger, that comes our title, invisible finger, right? So another advantage brought of our attack is that we do not need to analyze how this driving signal of different touchscreen controller and is how they are designed and what are the correct timing. Yeah, you need to measure that. You need to know, okay, this is line is what I'm going to detect, right? So we don't really need to do that kind of thing anymore. All we need to, as you can see that, we don't need to do any kind of encoding, and we don't care that what is the driving signal looks like. So we test our tech on different smart cell phone, tablets from different vendors, including Apple, Google, OnePlus, and even Microsoft. And we also show that all the devices vulnerable to our attack. While the previous timing-based IEMI injection, which was published before, and that only was tested on the Nexus 5, and so we increased our test bench largely. And another noticeable achievement of our attack also on certain time platforms, like for example, on iPad Pro and Surface Pro 7, we can even achieve we can even perform swipe gesture with any duration. So in general, our attack works better on iOS device than Android device. We think whatever the noise cancellation algorithm was employed on iOS touchscreen controller or just the OS driver level kind of actually makes our attack more efficient and more precise. So now we have a way to know what kind of EMI signal we want to use to perform a touch event injection. And we can also perform tap, press, and omnidirectional swipe and things like that with such signal. So, but everything is done by us just looking into the device and try to use our antenna to inject the touch event, right? So we're not even close to actually using this attack in real scenario. So then this is our third contribution. We present complete practical attack vectors. So a sequence, now we have established a theoretical background knowledge and actual setup, to induce the touch event, but we're still missing a really important part, right? So in real scenario, attack device probably is attached under the table, and the phone, if, for example, the victim walks towards the table and then places his or her cell phone directly on the table. And the phone will be randomly located. So as the attacker, we won't know that where the phone is located. And so in that case, we develop a phone locator techniques. And also for the attack scenario, there's multiple touches at multiple locations. And sometimes there is even a swipe gesture, this kind of like a gesture involved if you want to perform a successful attack. So in that case, we develop a touch event detector to resolve this issue. So as for the phone locator, a little bit recap on what the driving signal actually looks like on different devices. And we can see that for different row or column, the driving signal actually looks different. This applies to either sequential or parallel driving mechanism. And we can use this pattern to recover where the phone located. So we know ahead that how our antenna is located, how our antenna is organized, and we can use our antenna to measure what the signal looks like on the touch screen. And using these two information, combine these two information together, we can now use that to recover the precise location and precise orientation of the target device. And we can also see that if we are using more antenna, then the more accurate we can recover the phone location. For instance, like we are using 12 antennas simultaneously right now, and we can locate our target device without any displacement. So as for the touch event detector, we noticed that there's many of these smartphones will actively increase active scanning period when there's a touch event is detected, so it can make it runs a little bit more smooth and runs a little bit more accurate. So as shown in this figure, once we stop this type of EMI injection, the driving signal pattern that we measured from is actually different depending on whether this injection is successful or not. So this will tell you that the previous EMI attack is successful or not. So you can decide whether I should perform the next round of EMI injection to repeat that, or should I just move the antenna to a different place and then perform for the next stage of the attack. So combining all these different aforementioned techniques together, now we have achieved like a successful attack on the following scenarios. And you can find the detail of this kind of attack on our paper. So for the click-based attack, we have malicious application installation on Android device. We can also connect to malicious Bluetooth peripheral on iOS device. And for more complicated gesture-based attack, we can send messages, which involve with different keystrokes. And we can also use press and hold on PayPal icon to show the QR code. We can just scan it and then transfer the money, right? And more complicatedly, we can use omnidirectional gesture attack to unlock your cell phone if you're using gesture unlocking mechanism. And I'm pretty sure there's more interesting attacks which you can achieve using our techniques. But as for the mitigation, we propose and evaluate 2 mitigations in our paper. From vendor side, we can use pressure detection to decide whether they're a legitimate user touch. Or from the user side, a very simple Faraday fabric is totally enough to protect yourself from the EMI attack. So again, like all of our details, all our papers, our video demonstration is stored on our website. So if you're interested, there's more fun videos where you can watch. And so that'll be all for today. And thank you guys for listening to my talk. Please let me know if you have any questions or suggestions. All right?
All right, let's thank our speaker.
Thank you.
One really quick question for you.
Yeah.
So you mentioned being able to change or recognize the position of the phone.
Yes.
Can you actually recognize the type of device that you have? Because it seems like you have a variety of accuracies.
Yes.
That might change your result.
Right. That's a really good question because like as far we run tests around like 11 different type of device from different vendors, and as we can see that when we measure that, the driving signal that we can measure are totally different on different devices. So the moment you see that, you can just categorize that into certain device.
Fantastic, thank you. I just want to have one quick note before we take questions from the microphone. I've been trying all session to get the hop-in to work to take questions online, and I can't. So folks who are watching this online, my apologies. You're not being ignored. I just can't see you at all. So with that, we have a big line of folks here and plenty of time. Please ask away.
Yeah. Thanks for the talk. I'm Chen Wang from RSU. So have you already applied your attack to multiple finger touch?
So the multiple finger touch, what we do is like every antenna we use can be generated for like a single touch at single position. So the way we do for multi-touch is applying different antennas at different position and apply for the IEMI signal at different location. So we done that on iPad, we done that for the Surface, we done that on certain iPhone, but that's not really generic where we can use on, like for example, a lot of Android device yet.
So there's no interference?
There's no interference. Like we actually measure interference. Like the antenna distance, the minimum antenna distance can be around like 5 millimeter. And because like the shape of the antenna we use, so like they rarely cause interference between the IEMI antenna we use.
Yeah. So one quick question.
Yeah, sure.
So have you? So I wonder because the touch event can also capture the touch area and the touch pressure.
Yes.
Do you think that would be an easy way to
right, exactly. That's actually another way to mitigate this kind of attack. That's precisely, yeah.
Thank you.
Yeah.
Make sure you introduce yourself as you ask your questions.
Okay, hi, I'm Suryodaya from Penn State. So first and foremost, fantastic presentation and work.
Thank you.
And the first question that I had for you was, you said that the minimum distance between the antenna and the screen is 5 millimeters.
5 millimeter.
But
yes.
what's the maximum distance?
So the way we do this kind of like a multi-touch or anything like that is actually we build antenna array, as we also show on the video. Like we have antenna over here, we have antenna over there. And the maximum distance doesn't really matter. So it depends on what is the size of your target device and how many different channels of IEMI signal you want to apply on. So like the distance, the maximum distance, we don't really have a limitation for that. It's more or less like if we get too close, this antenna is going to interfere with that antenna, so makes the result is a little bit inconsistent.
Okay.
Yeah.
Awesome. And you mentioned that placing your entire setup underneath the table to attack on that. So I'm sure that you probably have some of this stuff on your demonstrations, but what kind of materials of the table have you actually tried this on?
Good question. Unless the table, we also done the evaluation in our paper as well. So unless your table is is made with some kind of metal, which will block this IEMI signal. Otherwise, wooden, acrylic, everything just works fine.
Okay.
Yeah. So the fundamental part is like your table cannot block the IEMI signal. That's it.
All right. All right.
Thank you.
Thank you so much for answering the question.
Hi, I'm Daniel Antonioli from Yier. And in your evaluation slide, you shown that you attack different platforms from different vendors. And I was wondering if you disclosed these attacks to the vendors, and what did they say?
That's a good thing. Where we think this type of attack, although we show how to practically attack, but there's still a lot of effort you need to do. It's not like you walk in some conference, you can expect that kind of thing happens. As you also notice that how giant our IF amplifier can be. So in that case, we think at this moment, we don't really see an emerging threat that people will be using this kind of attack to actually attack people. But more importantly, we think this is more or less how the touchscreen controller vendor instead of how is a smartphone vendor, because they normally just purchase this kind of solution from Atmel, from Max Touch, this kind of a vendor. We did talk with some of them, and they think it's just a matter of whether they want to use a more advanced noise elimination algorithm or not. But they don't really think this is an attack. They just say, yeah, this is a type of interference, but that's it. Yeah.
So yeah, the practicality of the attack is kind of
right. Yeah.
And if you go back to the slide about the attack scenario.
The attack scenario.
The attack. Yeah. So I was wondering, how are you detecting when you can, send this malicious click to install an app?
So I see.
In that case, and second question is, sometimes when you have to do.
Sorry to interrupt. We have about 30 seconds left, so if you want to get maybe one of those questions in, that'd be great. And then please chat with the speaker afterward.
Right.
So
So for the malicious application installation, what we do is we actually send so that's our assumption. We know the target device, the phone number, so we can just send a message over there. And over there will be a preview where we can know this preview is actually located, and then we just inject the touch event at that precise area. Then we can just open that event, open that window, and then try to proceed for installation. And this is definitely complicated because we measure that there probably are 5-6 distinct touch events should be involved. And so you have a 6 or 5 antenna placed at different location to inject this touch event one by one at different location to eventually install this type of application.
All right, thanks.
Yeah.
Folks, let's thank all of our speakers. This is the